Hello and welcome to Bitcoin Explained, where I break down some of the more technical aspects of Bitcoin in a simple way. In this video, I'll be teaching you about elliptic curves over finite fields, and it's actually the third video in a 5-part series on the cryptography behind Bitcoin. Elliptic curves over finite fields combine finite fields and elliptic curves over real numbers, which we learned about in the first two videos of this series. And it's really what's at the heart of the mathematics behind elliptic curve cryptography, the cryptography that Bitcoin uses. Once you understand what I cover in this video, you understand all of the mathematics that's required to understand Bitcoin's curve, how you do transaction signing and verification on the Bitcoin blockchain, and a lot of other cool stuff. Now with all that said, let's talk about elliptic curves over finite fields. In this video, I'll once again be sharing my screen and showing you a Jupyter notebook. The Jupyter notebook once again allows me to visualize what I'm talking about a lot, because elliptic curves over finite fields, just like elliptic curves over real numbers, in my opinion, are best understood visually and intuitively rather than just looking at the abstract mathematics and some formulas. This video will be split into 4 sections. First, I'll be visualizing elliptic curves over finite fields and showing you what they actually look like over a graph and why they look the way that they look. Then I will talk about point addition over finite fields. Remember, point addition is what we did for elliptic curves over real numbers. Now we'll be doing it over finite fields. And then we'll move on to point multiplication, which builds upon the logic of point addition, similar to elliptic curves over real numbers as well. And then lastly, I'll be teaching you about one really important problem or property of elliptic curves over finite field, which is called the elliptic curve discrete logarithm problem. All right, let's get started. Okay, let's actually visualize an elliptic curve over a finite field. For this example, I've chosen the following elliptic curve. Y squared is equal to x cubed plus 8 over the finite field of order 127. 127 is a prime number, and when we actually compute all of the points that fall onto this elliptic curve over this finite field, meaning we get all of the x and y coordinates that satisfy this curve equation here, and plot them on a scatter plot, then what we get is the following. Now, this looks completely different to the visualization of the elliptic curves over real numbers that we saw. As you can see, this is just a scatter plot, meaning they're just some blue dots on this plot, but there's no curve. So how is this an elliptic curve? We don't have the smooth graph anymore, the continuous graph that we had for elliptic curves over real numbers. That's the first thing to note. Let's look at this scatter plot a little bit, and then I'll explain why it looks the way that it looks in a second. Now, a few other things that you might notice are that both the x and the y coordinates are 0 or positive, so there aren't any negative values. And you might also notice that they are bound to be between 0 and somewhere above 120. One other thing that you might notice when closely looking at this is that there seems to be some symmetry in this scatter plot, and the symmetry appears to be somewhere around this axis here. So there's some kind of imaginary axis right in the middle of this scatter plot about which there is some symmetry. As you can see, a lot of these points are basically just mirrored over this axis here. Now, why is all of this the case? Why does this look the way that it looks? Why don't we have a smooth, continuous graph anymore or curve anymore? Why do we only have a few points in a scatter plot and that is the entire elliptic curve? Now, the reason for that is that we're not dealing with real numbers and a coordinate system with real numbers here anymore. We're dealing with finite field elements. And as you remember from the video about finite field elements are only allowed to be integer values, and they're only allowed to be in the range from 0 to p minus 1. Now in this case, because the order of the finite field is 127, the x and y coordinate values are only allowed to be integer values, and they're only allowed to be between 0 and 126. Meaning that only certain points that have integer and like really clean integer coordinate values for x and y coordinates and that fall within the range of allowed values will actually be valid points that satisfy the curve equation over finite field elements, which is why we don't get a curve anymore, we don't get a continuous graph anymore, but this is still the representation of an elliptic curve just over finite field elements. Remember, we're doing abstract mathematics here, so this is a little bit abstract, but the cool thing is, and I will show this later in the video, that despite this looking nothing like the elliptic curve over real numbers, all of the intuition and the logic behind the math of things like point addition and point multiplication are actually exactly the same, and they still work exactly the same, which is kind of miraculous because it doesn't look anything like it, but it still works. We'll see how that works in a second. Now, before I move on to talking about point addition and point multiplication, let's get a bit more of an understanding of how maybe even the same elliptic curve just over a finite field of a different order would look like, and how the order of the finite field changes the points on the curve. So I've done exactly that using some Python code here. I'm always using the same elliptic curve, so y squared is equal to x cubed plus 8, and I'm just choosing different orders of the finite field that they are over, from 11 to 31 to 41 to 89, and visualizing all of the scatter plots or the resulting points that satisfy the elliptic curve over the finite field of that respective order. For the order of 11, we get this scatter plot here. You can see there's only a handful of points that actually satisfy the elliptic curve over this finite field. For the finite field of order 31, we get this here. There's a lot more points. For 41, we get this here. And then for 89, we get this scatter plot here. Now they all share the same properties, meaning that they all have x and y values that have to be from 0 to p minus 1. And they all have this symmetry as well. Now, one thing that I haven't touched upon is why this symmetry is there. This is similar to how we get the symmetry for elliptic curves over real numbers. It's just that the symmetry there is at y equal to 0 or around the x-axis, because we've got the y squared term on the left-hand side of the elliptic curve equation, meaning that there's usually always two y values for a certain x value because of this y squared on the left-hand side. But because we're dealing with finite field elements here, we can't have any negative values for the y coordinate anymore. So we can't actually have the symmetry at the x-axis or y equal to 0, meaning that there's a positive and a negative value for y for each x value. Here it needs to be in the middle of the area of the curve, which actually happens to be p divided by 2, so the order of the finite field divided by 2, and it's basically just shifted to be above the x-axis and still happens in the middle of the curve, so to say. Now, before we actually talk about point addition, let's try to build a connection between these elliptic curves over finite field elements and elliptic curves over real numbers, because there actually is a connection. It's not completely straightforward, but using a specific example, I'll explain to you how you can actually map some of the points on an elliptic curve over real numbers to points on the same elliptic curve over finite field elements. To do this, I've chosen the following example, which is y squared equal to x cubed plus 8, same elliptic curve, over the finite field of order 11. Now, we've already seen this scatter plot, but just to show it once again, we get all of these points that lie on the curve over this finite field here. Now, one thing that we can actually see is that if we plot the same elliptic curve over real numbers instead of finite field elements, then the point 1, 3, which clearly falls on the elliptic curve over this finite field, and the point 2, 4, which is also one of the points that lies on the curve, are both also on the elliptic curve over real numbers. Now in this case here, I'm showing the point 1, 3, but the point 2, 4, as you can roughly see, is also on this elliptic curve. Now, in this case, this is the case because these are both points that have perfect integer coordinates for both x and y, and those integer coordinate values for x and y are both below 11, which is the order of this finite field, which this is over here, meaning that if we do all of the computations modulo 11, then both 1, 3 and 2, 4 modulo 11 just remain 1, 3 and 2, 4. So those points are actually integer coordinate value solutions for both the elliptic curve over real numbers and for the finite field. But there's another interesting point that we can look at, which is the point 46, 312, which on the elliptic curve over real numbers, as you can see, falls on the curve here. So it's 46, 312 are the coordinates. But now here's the interesting thing. 46 and 312 modulo 11 are actually congruent to 2 and 4, meaning that when you basically take the values of this x and y, of these x and y coordinates of this point here and compute them modulo 11, then they collapse down to 2 and 4, because those are the remainders after dividing the x and y coordinate by 11. Meaning that for the elliptic curve over the finite field of 11, this point here with coordinates 46 and 312 is actually congruent to the point 2, 4, which is also on the same curve. So there's two different points that when we collapse the entire space of infinite points on the elliptic curve over real numbers into the finite number of points on the elliptic curve over finite fields, then we collapse multiple different points from the elliptic curve over real numbers onto one point for the elliptic curve over the finite field, this point 2, 4 here. So this point here is sort of like how in finite fields we had buckets or slices or elements of the finite field that technically are congruent to many other values that fall outside of the range of allowed values for the finite field elements that just get collapsed into one of the buckets in the finite field by doing the modulo operation. Same concept here. This is how you can link elliptic curves over real numbers to elliptic curves over finite field elements. Now that we understand this link, we can actually move on to point addition over a finite field. Before I show what point addition over a finite field looks like, let's quickly recap and look at what this looked like for elliptic curves over real numbers. So in this case, if we wanted to add 2 points that lie on the curve and aren't the same point, then for A and B, for example, then what we did is we got the straight line that connects these 2 points and then found the third point on the curve that as long as these 2 points are not the inverses of each other and this straight line is perfectly vertical, there will always be a third point. We talked about this in the previous video. There's a mathematical proof for that as well. But anyway, so we find the third point where this straight line intersects again and then flip over the x-axis. And remember, the x-axis here is the axis of symmetry. And then where that point then ends up is basically the inverse of the third intersection, and the result of A plus B is down here for elliptic curves over real numbers. Now for elliptic curves over finite fields, the logic is exactly the same, it just looks slightly different. So if we have this scatter plot, in this case I'm using the same elliptic curve over a finite field of order 19, and we want to add 2 points, A and B. Then the logic for doing the point addition is once again, find the straight line that goes through the 2 points that you want to add, A and B, and then find the third point where this straight line intersects the elliptic curve. Now in this case, we are limited to the x and y space from 0 to 18 because we've got the order of 19, so p minus 1 is the highest value, so 18. But what happens here is that when we draw this straight line through A and B and it hits one of the borders of the possible values, which could be 0 or 18 on both the x and y axis, then we just wrap around to the other side of the axis where it hit the limit and continue the straight line with exactly the same slope. So you can see we get the straight line through A and B, hit the limit here, we wrap around to down here, same slope, straight line, still haven't found another point, we hit the limit up here, go down here, we just missed the point that's down here, and then the straight line with the same slope. Now it hits the 18 on the x-axis, so it wraps around to the other side of the x-axis, starting at 0, still continues with the same slope, hasn't hit a point yet, wraps around at the y-axis, back down to 0, same slope, and then it finally connects to a third point on the elliptic curve, this point C here. And then once we find that point, then all we need to do is we need to reflect over the axis of the mirroring axis, which, remember, for finite field elements isn't the x-axis anymore, but it's the axis that's right in the middle of the finite field. So here we have a finite field of order 19, so 19 divided by 2 is 9.5. So the axis of symmetry is somewhere around here, and when we reflect this point over the axis of symmetry to get the other point on the inverse of this point, the result of A and B is down here. So the logic and the intuition behind doing the point addition for an elliptic curve over a finite field is exactly the same as it was for the elliptic curve over real numbers. It's just a bit more abstract, but it works exactly the same, and the interesting thing is the mathematics to compute the slope of the straight line and all of that stuff still works exactly the same. We're just doing modular arithmetic here, but the logic is exactly the same. And if you write a good Python library, like I've done to do all this, where all of the values that you use, so even A and B, and all of the coordinates for the elliptic curve points that you want to add are finite field elements, and you construct this class in a way in Python, for example, where it handles finite field math using modular arithmetic, then this becomes really, really easy to do and visualize. So that's how point addition works. Now let's talk about adding a point to itself. So if we take the point here, point P, with coordinates 11 and 16, and we want to add the point to itself. Before we talk about that, let's quickly recap how that looked over real numbers again. I'm gonna have to scroll down a little bit. Adding a point to itself. So again, over real numbers, the way that this worked was that instead of connecting two different points, we thought about this similar to bringing 2 points infinitesimally close to each other until they become the same point. And then we just need to find the tangent line to the curve at that point that we want to add to itself, and then find the point where that tangent line, which is a straight line, and which we've proven needs to intersect the elliptic curve again. We find the point where that straight line, the tangent line, intersects again, and then mirror over the x-axis or the axis of reflection or mirroring, which in this case is the x-axis for real numbers, and for finite fields that will be p divided by 2 right in the middle of the scatter plot. And then we get a added to itself to be down here. Now for elliptic curves over finite fields, once again, logic is exactly the same, the intuition is exactly the same. This is the beautiful thing about abstract mathematics. If you construct the field and the field elements to all follow the properties that we talked about in finite fields and elliptic curves, then all of the math will still work exactly the same, just a bit more abstractly to visualize. So here we've got the point P with coordinates 11 and 16. Now to add this point to itself, we just need to find the straight line that's tangent to this point. Now, visualizing this is a bit difficult because we don't have a smooth plot here, so there's not really a tangent line that we can draw, but the math, like I said earlier, is exactly the same. So we just compute the slope of the tangent line the way that you compute the slope of any tangent line to a curve. And then once again, we take this straight line until it intersects or hits another point that falls on this elliptic curve, and then reflect over the reflection axis. So for this point P, that just means we take the straight line up here until it hits 18, wrap around, it just passes through these 2 points, hits the limit again, wraps around, and then finally it intersects another point on the curve, and then we just reflect over this reflection axis, which would be here at this point, and then get the result of adding this point P to itself down here. Beautiful. This all works exactly the same as we learned previously. Now that we've seen how you can add a point to itself, let's talk about point multiplication over finite fields. We're finally ready to talk about point multiplication over finite fields. Before I show you how this works over finite fields, let's quickly recap once again how we did this for elliptic curves over real numbers. Now, we didn't necessarily visualize this too much. We just walked through how you can do efficient addition or repeated additions, which is what point multiplication in the end just is. The one thing that we did do is we visualized taking the same point A added to itself to get 2A down here, added to itself another time to get 3A down here, to visualize that point multiplication is just repeated point addition, or adding a point to itself a given number of times. Now, for elliptic curves over finite fields, this works exactly the same way. Now, if we use the same point that we used to add to itself above with the coordinates 11 and 16, and we point multiply that point to itself a given number of times and visualize how often we point multiplied it, we get the following scatter plot. Now here it's important to remember that 1 is equal to just the point itself, 2 is equal to the point added to itself once, which gets us down here, and 3 is equal to the point added to itself twice. So 3p is p added to itself twice, so that might be a bit confusing, but that's just how this works. So what we then get if we point multiply this point a given number of times are all of these points down here. Now what you can see is that the highest number or the highest point multiple next to any of the points here is 13. But if you remember what the elliptic curve over this finite field looked like up here, it seems like there's a few points that were on the elliptic curve over the finite field that we don't have in this plot here. And why do we stop at 13? What happens if we want to go past 13? So if we go past the value 13, then what happens is we wrap around and start again at the same point that we started with. You can see there's a number 15 here. Now, the reason for that is that for an elliptic curve over a finite field, every point on the curve has its own order in a way. Now, the order is defined as the integer value that you need to point multiply this point by to get the point at infinity. This sounds a bit complicated, but I'll explain this. So for this starting point here, you can see the 1 next to it as well. When we point multiply it 13 times, we get this point down here. But then as soon as we add it to itself one more time, so point multiply it to itself 14 times, we actually get to the point at infinity, which we also call the point that is nowhere, which we can't visualize in this curve here because it's the point that's nowhere. And then as soon as we add it to itself once more, so if we add the original point to the point at infinity, the point that is nowhere. We start again at the same starting point. And then if we add it to itself another time, we get to the same point as 2. If we add it to itself another time, we get to 17, which is also 3. So once again, there seems to be some cyclical pattern in this, which we are used to from finite fields. And there's also, I guess, a little bit of congruency of these points, as we showed earlier, how you can map different points over elliptic curves of a real number to the same point on an elliptic curve over finite fields. Now, if we choose another point from the same elliptic curve, let's choose the point 2 and 15, which you can see on this curve here is on the curve. Then what happens is you get the starting point here, 2, 15, and then when you add it to itself once, you get this point here. When you add it to itself another time, you get this point down here, and when you add it to itself, you get this point, another time you get this point here, then here, then here. Then you get the point at infinity, and then you wrap around another time to the starting point up here. But that's really interesting, because now, depending on which point from the original elliptic curve we chose, if we point multiply it with increasing integers, we can only generate a subgroup of all of the points that we had on the entire elliptic curve over the finite field that we started with. And why does this happen? Well, so the reason that this happens is that, like I said, each point on the elliptic curve over the finite field has its own order, and that order can be different to the order of all of the points that fall on the elliptic curve over the finite field. So the original curve that we had here, let's look at that, has a certain order, which isn't actually 19. That's the order of the finite field. That's different. The order of the group of points that fall on this elliptic curve is how many points we actually have on this elliptic curve, which is 27 in this case. So we can have 27 different points. So 26 different points plus the point at infinity for the entire group of points that satisfy the curve equation. But then if we choose some of the points that fall on this curve and point multiply them, we're not able to generate all of the other points that fall on the elliptic curve, but only a subgroup of them. And that subgroup, or how many other points we're able to generate on that same elliptic curve using point multiplication of the starting point, is the order of that point. But if that order isn't prime, then what happens is when we point multiply this starting point by increasing number of integers until we get the point at infinity, we reduce the possible size of the group of elements that we can reach by using that starting point and point multiplying it a lot. In this case, not as much as in this case down here. Now, why is this important? In elliptic curve cryptography, we need something that's called a generator point. A generator point is a point from the elliptic curve over the finite field which can either generate all other points on the elliptic curve over the finite field or almost all other points on the curve, which is only the case if the generator point, or the point that we start with, has an order that is the same or very close to the order that the entire group of points on the elliptic curve has, and that order has to be prime. As you remember from the video on finite fields, if we do multiplication of every element in a finite field and the finite field doesn't have a prime order, then we collapse the size of the finite field if we do the multiplication by one of the divisors of the order of the finite field. So we need a prime order, and we need it to be ideally very large and very close to the order of the entire group of points on the elliptic curve over the finite field. Now let's actually have a look at an example of that. So in this case, I've chosen the elliptic curve y squared is equal to x cubed plus 28x plus 1 over the finite field of order 29. When we plot all of the points that satisfy the elliptic curve equation over this finite field, we get this scatter plot here. Now let's just pick any of the points, let's say 5 and 18, and use that as a starting point to then do the point multiplication. If we do that, we've got the starting point here, and then we add it to itself once to get the point over here. Then we add it to itself another time to get the point over here, and then you can step through that. But what you will see, and I'm trying to find the number right now here, the highest multiple that you will see in here is 36. This means that because the original group also has 36 points plus the point at infinity, this starting point here with coordinate 518 is actually able to generate every other point that falls on this elliptic curve over this finite field through point multiplication using increasing integers. And then if we choose another point, let's say 12 and 21, the same thing works again. So using this point as a starting point here, we can add that point to itself once to get the point down here, then we get to up here, and then we move on until we get the number 36, which in this case is down here. Meaning that both of these points are really good generator points because they both have the same order as the full group of all of the points that fall on this curve. And then if we want to add it to itself more than 37 times, what happens is we wrap around to the same point again. So 1 becomes equivalent or congruent to the point 38 on the curve. Now, why does this matter? Why is it important that we have a good generator point? Now, one of the key reasons for this is that we want to be able to do point multiplication using increasing numbers or increasing values of integers using a generator point. So in Bitcoin, we have a generator point. I'll talk about all of this in the next video, but this is a little preview. In Bitcoin, we have a generator point, which is a point on an elliptic curve over a finite field. We just have an elliptic curve over a finite field with an order that is really, really large, astronomically big. And then that generator point is the same for everyone. And then we generate a private key, which is just a really large integer, essentially. You'll learn more about this in the next video. And then point multiply the generator point with that really large integer. And the point where we end up with, that becomes our public key. But now what's important is that for the security of Bitcoin and for the security of the private public key cryptography, there needs to be a guaranteed one-to-one mapping from the generator point to the number that you use to multiply to the public key. And the reason why we want to have this one-to-one mapping is so that there are no private keys that when multiplied with the generator point lead to the same public keys. But that's only possible if we have a really large finite field, because as soon as we get a small one, there's not enough space in this elliptic curve, or there's not enough points on this elliptic curve. But also we want to restrict the value of the private key to be smaller than the order of the generator point. Because then if we have that, we never have this wrapping around. So we never have this congruency of one point to another point, or one multiple of a point to another multiple of a point. Because remember here in this case, these multiples 1 and 38 would be the private key that we use, and we don't want the same private or different private keys to lead to the same point, which is actually what the public key is. So in Bitcoin, as long as we have something like this here with a really good generator point that's able to generate a lot of the points or all of the points that fall on the elliptic curve through point multiplication using different integer values, and as long as the finite field is really large, then this is really secure. Another reason why we want to have something like this is that point multiplication on elliptic curves over finite fields actually distributes points uniformly over the elliptic curve. This means that this appears pretty much random, meaning that if you only know the starting point, so this point 1 here, and somebody else gives you just the coordinates of this point down here, which is the point of point multiplying the starting point 22 times, but they don't tell you the 22, then there's no way to back solve for this number 22 here, because this isn't easily predictable. This is basically what's considered a one-way function, and there's no way of reversing point multiplication on an elliptic curve over finite fields because it's so secure and uniformly distributed, meaning that if somebody wanted to find out how many times this point was multiplied to get from the starting point to the point down here, the only way to do it would be to brute force it, which would be to loop over every possible integer value that could be used for the point multiplication until you get the point down here. And then you can say, it had to be 22, which in Bitcoin would be a private key. So somebody could backsolve for your private key. But because we're using elliptic curves over finite fields that are so large, it's computationally completely infeasible to go through every possible integer value and actually break the private public key cryptography. We'll talk a lot about this in the next video, but this is a bit of a heads up as to why this is so important. So what I just explained here is actually what's called the elliptic curve discrete logarithm problem. So I've basically already described it, but let's look at it formally and then I'll go back to talking about what this really means. What the elliptic curve discrete logarithm problem states is that given a point P, so a starting point, and a multiple of it, Q, where the multiple is just K multiplied, or P multiplied K by K, or added to itself K minus 1 times, where K is a secret integer, the challenge is to find K. So basically finding 22 by only having the starting point P here and the resulting point Q here. Despite knowing both P and Q, computing K is computationally infeasible for a large K. And this is what makes elliptic curve cryptography so secure. So what I just explained before is exactly what makes this so secure. There is no mathematical way to solve for 22 given the starting point and the ending point. You have to do it using brute force. And if you start having elliptic curves over finite fields with orders of magnitudes that aren't even in the billions or trillions, like we're talking way larger orders of magnitudes, as you'll find out in the next video, then this becomes completely impossible and you're probably more likely to win the lottery 10 times in a row than to solve for private key successfully. Now, to finish up the video, I want to talk about one other thing that's quite interesting and important, which is why do we actually do elliptic curves over finite fields? Why don't we just use elliptic curves over real numbers, the ones that we learned about in the previous video? There's basically 5 really important reasons for that. The first one is that over real numbers, operations like point addition and multiplication can lead to points with coordinates that require infinite precision to represent them accurately. This complicates the computation, but can also complicate the storage of the values, but also can lead to different results on different machines and using different programming languages, for example. Whereas if you only use integer values and modular arithmetic, which is what we do with finite field elements, then everything is just integer values and it becomes really discrete and predictable and also repeatable. This is similar to the efficiency of the computation. So efficiency goes up a lot when you do finite field mathematics because you use modular arithmetic for operations like addition, multiplication and division, which can be computed a lot faster this way. In terms of security, the good thing about having elliptic curves over finite fields is that for a finite field, the size of the field, so the number of the elements in the field, directly influences the security of the cryptography that you use, meaning that a larger size of the field means that you have to brute force more possible integer values in order to backsolve for something like the private key or the point multiple that was used to get from a starting point to an end point. And then once again, if you use a really large finite field size, then this becomes really secure and basically unbreakable. The uniform distribution, as we talked about, so the finite field structure ensures that points generated by point multiplication are uniformly distributed across the curve, which contributes to the security because it's super random and there's no predictability in it. Then the deterministic operations, using finite fields makes all of the operations on elliptic curves completely deterministic and repeatable, which is super, super crucial for the cryptographic protocols that we use in Bitcoin and other cryptography applications, because you want to be able to always get to the same public key if you point multiply the generator point by a certain private key, but you also want to be able to really verify the signature of a transaction using a public key, and always everybody across the network should always get to the same result, and this is guaranteed if you use modular arithmetic and finite field elements. Now, just to make a point about the discrete and predictable here, in Python, for example, if we were to use real numbers and not restrict ourselves to finite field elements or integer values, then if we did something like take the number 8 and compute the square root of that, we would get this floating point value down here, which would technically require infinite precision to store, but Python doesn't do that. So what then happens when we square this square root again is we don't actually get back the number 8, but we get 8.000 and so on 2, meaning that this isn't actually 8. And this result could be different for different computers using different levels of precision, different computer programs, so Python versus C++ or something like that. And that's why we don't use any real numbers for the cryptography in Bitcoin, because it can just lead to these complications. And doing everything using integer values or finite field elements and modular arithmetic is way more discrete, predictable, and secure, and that's why we do that. Okay, you've now understood everything that there is to know about elliptic curves over finite fields, and we can finally talk about the actual curve that Bitcoin uses. I'll see you in the next video.